Hello everyone. Today we are going to discuss about flow batteries. A flow battery is a rechargeable system that stores energy in liquid electrolytes kept in external tanks. These liquids are pumped through a central stack where the energy is either charged or discharged. What makes it unique is that power and energy can be scaled separately, offering a lot of flexibility. It's also safer, has a long life, and is perfect for large-scale energy storage, like supporting renewables and stabilizing the grid.
Now, let's take a closer look at what happens inside a flow battery. Electrolyte solutions containing dissolved electroactive species are stored in external tanks and pumped through a central power cell where the core electrochemical reactions occur. Inside the cell, chemical energy is converted into electricity through redox reactions. These reactions are fully reversible, allowing the battery to be charged, discharged, and recharged as needed. One of the key advantages of the flow battery is that energy capacity and power output are handled separately. The amount of energy stored depends on the volume of the electrolyte, while the power output is determined by the size of the cell's active area. To keep everything balanced during operation, a membrane inside the cell allows ions to pass through the two electrolyte streams, maintaining electrical neutrality without mixing the fluids. Let's take a quick look at the key design considerations for a flow battery. First, the electrolyte must be redox active with high solubility chemical stability and good reversibility to support efficient and consistent charge discharge cycles. Next, the membrane plays a crucial role. It needs to selectively allow ion exchange while preventing cross contamination between the two electrolytes to maintain system efficiency. The flow system, including pumps and piping, must ensure smooth and uniform circulation of the electrolyte. It should minimize pressure drop and energy use while maintaining consistent flow throughout the cell. Volume capacity is another critical factor. Since the amount of stored electrolyte determines total energy, the tank size must be designed to meet the specific energy requirements of the application. Finally, scalability is essential. Flow batteries should allow easy scaling of power through cell stacks and energy capacity through tank size, making them suitable for both small and large scale energy storage needs.
Let's briefly explore how the electrical double layer impacts flow battery performance. At the electrodes, it affects current and overpotential behavior captured by the Butler-Woomer equation. Reaction rates in porous electrodes are directly influenced by the double layer structure. In the membrane, the double layer forms a dominant potential which controls ion migration, species crossover, and ultimately affects Coulombic efficiency. For electrolyte flow, the double layer creates a zeta potential which influences electroosmotic flow. This impacts pumping losses, pressure gradients, and mass transport within the system. When designing a flow battery, several key equations help define its performance and operation. The Nernst equation determines cell potential based on concentration differences. Faraday's law relates total charge to current and time. Capacity is calculated from moles of electrons, Faraday's constant, and cell voltage. To assess energy per volume, we use volumetric energy density, which divides total energy by electrolyte volume. The Darcy-Weisbach equation helps estimate pressure drop in the flow system. Mass balance equations help track changes in electrolyte concentration. Finally, pumping power is calculated from pressure drop, flow rate, and pump efficiency.
Now, let's take a look at scale-up methods for a lab-based flow battery to real-time systems. First, scalable design allows power and energy to scale independently through stack and tank size adjustments. Flow optimization with advanced flow field designs improve electrolyte distribution and reduces losses. Efficiency is crucial at larger scales, so minimizing pumping losses is a key focus. Cost control involves reducing the cost of membranes and materials. Finally, safety and durability are enhanced with aqueous electrolytes and long-lasting components.
Designing flow battery stacks involves several key factors. Cell architecture focuses on minimizing shunt currents with bipolar plates. Membrane selectivity is critical with options like naphion or anion exchange membranes. Electrode porosity is optimized with materials like carbon felt for better kinetics. Flow field design ensures uniform distribution. Sealing integrity is maintained with EPDM or fluoropolymer gaskets. Corrosion-resistant current collectors are usually titanium or durability. Stack combustion ensures Mechanical stability, while thermal management and pressure drop minimization are addressed through hydraulic design. To design an efficient flow battery, it's essential to grasp the key principles that drive its operation. This course is designed to help you build that understanding and apply it in real world battery design. The course provides a strong foundation in the chemical reactions, kinetics, and thermodynamics that govern battery performance. Understanding these principles is crucial for designing a battery that functions efficiently over time. It also dives into mass and charge transport, which are fundamental for optimizing flow fields and ensuring the proper distribution of electrolytes. These concepts are key to minimizing losses and improving overall efficiency in a flow battery system. Lastly, the course guides you through selecting the right membranes, electrodes, and electrolytes. You will learn how to balance performance, cost, and safety to create a reliable and cost-effective battery.